Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 36 of this course on machine learning for art system science. We are currently in module 5, the last module, where we are dealing with how machine learning can be used for art system modeling, and the topic of this lecture is physics based machine learning for process models. So the different concepts which we are going to cover here are physics inspired machine learning, and how we can emulate process based models using this PIML, and we will also see one specific application of PIML in lake temperature modeling. So first of all, what is this PIML all about? So we have like in the last lecture we were considered process based models versus statistical models. Now these process based models are used in various art system processes for simulation. Now these suffer from multiple challenges, like suitable parameter values are often not known, the computations are very expensive, require a lot of time and a lot of computing power and so on. So now in what ways can machine learning alleviate such problems? So one approach is to develop such models which can emulate these process models. That is to say, you do not really need to run these process models. The key here is that most of these models are deterministic. That is, if you set certain initial conditions, it's determined, that is, there can only be one particular output or final conditions that can arise. The question is what that will be. So this can be considered as something like a machine learning problem, which is to map the initial conditions to the final conditions. So we can aim to train a machine learning model which will simply be able to predict what the model will or it will be able to predict the predictions by the process based models. That is, if you give the initial conditions, then your machine learning model will be able to predict what will be the values of the final condition which the process based model will come up with. So that is called emulation of these process based models. And a second approach is to develop a machine learning model to estimate suitable parameter values that map a given predictor set to a target value. That is, that's a more principled way of estimating the parameters, instead of some experts specifying the parameter values and using that same parameter values all the time. This approach is, here you let us say we already know the initial conditions as well as final conditions. How we know? That's from the observations. Then we will see whether the model is actually able to map those initial conditions to the final conditions, and if so, for what values or what settings of the parameters. So that is the way of data driven parameter estimations. Now these kinds of models or machine learning based models which we are talking about, one obstacle of using machine learning for such problems is that their outputs and also the different internal values which they generate, they may not be consistent with the laws of physics. By internal values, I mean, suppose we have a machine learning model which consists of different variable which deals with different variables of the process. So if we are simulating over a particular time sequence, at different points of times the values of those variables will be estimated and so on. Now those estimates may not be consistent with the laws of physics. So the solution to this is to define a physics based loss function that measures the violation of the physics laws. In recent times there is this paradigm called physics informed neural networks which has emerged, and this is a famous paper which uses these physics informed neural networks, that is a deep learning framework for solving forward and inverse problems involving nonlinear partial differential equations. So, most of the process based models are actually based on differential equations, that is, I already mentioned governing equations in earlier model, so earlier lecture. So, often those governing equations are actually differential equations. So, what this paper talks about is like using a deep learning framework for solving these kinds of differential equations. And to solve like one we can say one technology which becomes very relevant in solving these differential equation problems is that of automatic differentiation. Now, this is what a physics informed neural network looks like. So, let us say that just focus on these two things. Let us say that there are two variables sigma and this lambda, and both of these are dependent on time, and there is a particular parameter called gamma. You can treat it as something like a model parameter. So, let us say that these are the governing equations of the model of the process based model. So, that is d sigma dt, the time derivative of the variable sigma is some function f1 of sigma at that point, lambda at that point, and the model parameter gamma dot. And similarly, for the time derivative of lambda, that is also another function f2 of the same thing, sigma, lambda, and gamma dot. So these are the two model equations which specify the process based models. So the process based model will of course start with some initial values of these quantities, and at every given point it will calculate these derivatives and then update the two variables, and then based on that at the following time step again it will do these and so on. So but the time steps that are being considered here are of course infinitesimal. So if I have to, even if I have to simulate for a particular, let us say 5 seconds or something like that, to for that simulation it will have to carry out so many of these variable updates, because at every step it is the time is advancing by only an infinitesimal step. So so that's going to take of course a lot of time, and this is still a very simple model. In case of neural network, what we will aim to do is, like, we will specify the time and we will specify the model parameter. The neural network really needs to predict the values of sigma and lambda at that time for that value of the parameter. Okay, so the neural network is of course the universal function approximator. So f1, f2, all these functions it should be able to approximate, provided it is trained with a lot of data. But whatever values it estimates, that is sigma and lambda, can we really guarantee that it will be following these two constraints? That is, can we say that d sigma dt will actually be equal to this function and d lambda dt will be equal to this function? That in general we cannot say. So what we will do is, once we get the values of sigma and lambda being produced by the neural network, we will actually calculate d sigma dt and d lambda dt from the generated values using automatic differentiation, and we will also actually compute these functions. So based on that, we will actually calculate these two losses, R1 and R2. So as you can see, R1 is how much the estimated value of sigma, that is, for the estimated value of sigma, are these two equal or not? If they are not equal, then what is the error? Similarly, for lambda also, are these two things equal or not? If they are not equal, then how much is the error? So if sigma and lambda are different, the predicted sigma and lambda are different from what they should be, then of course these errors will be large. So accordingly, we need to update the values of sigma and lambda. And how will such update happen? The update will of course happen if we change the different weights of the neural network. So we will define this kind of a loss function, which which will help to update the weights of the neural network. So in this case, the loss function will include this physics loss. that is which is measuring how much by how much the predicted values are differing from what they should be. So like there are now two different kinds of loss functions. One is the usual loss, where we are simply comparing the simulated values of sigma and I mean the predicted value of sigma and lambda with what the process based model would have given, like if we had actually solved these differential equations and till the time t and obtained the values of sigma and lambda. So let us call those as sigma hat and lambda hat. So one part of the loss function is coming by comparing sigma with sigma hat and lambda with lambda hat. The other part of the loss is coming from the physics based loss, which is basically calculating by how much these two like whether these two equations have been satisfied or not, and if not, then what is the amount of error. So like we can say the prediction loss as well as the physics loss. So these two things like as you can see, this is the loss function. So the loss function is getting its input from two things. One is from the sigma and lambda themselves, that is the prediction loss, and the other is from these R1 and R2, that is the physics loss. So these two things are combined and to get a new loss function, and based on the and it is this combined loss function that we try to minimize through backpropagation and so on, by which we update the different weights of the model till we have been able to get the optimal set of weights. So that is how the this PINN or physics informed neural network works. So in this lecture and also in the following lecture, we will see several applications of this kind of idea, where we will see the loss function of a machine learning model being used to capture some kind of physical constraint like this. So in today's lecture, we will consider one particular application of lake temperature modeling. So suppose there is a lake, I want to estimate the different temperature, I mean the temperatures at different heights of that within or depths within that lake. Of course, I cannot measure everywhere, so I have only a few in situ measurements at the different depths and different locations. I want to get the temperature profile of the entire lake. Now the first thing is there is a process based model, because as I said there are only in situ measurements, so we do not have the full data. In the absence of the full data, we have to depend on what is simulated by a process based model which the experts have developed over the years. So this is what the process based model which we are talking about. It's a general lake model, also known as GLM. It is used to it is basically developed using some for one particular lake, which is provided with lots of sensors at different locations and so on, but the aim is to apply it for any lake. So this general lake model, it is it's a very highly complex elaborate model with multiple layers. So these are the different layers which are mentioned: the water balance, the surface energy balance, the snow and ice dynamics, and so on. Of course, this is not relevant to many lakes, especially those in the tropical regions, but in the extratropical regions where ice forms in the lakes, this is an important thing. Apart from that, sediment heating, stratification and vertical mixing, inflows and outflows, the wave height and the bottom stress, as well as the lake will have its own living organisms living in it, the plants and other which have grown all over. So so there is some kind of biogeochemistry also involved. So the interactions of the lake's water with this ecology and biogeochemistry, these are also taken care of by some model. So typically this is a schematic diagram of the lake model. So as you can see, this is a lake. So first of all, there are some external factors like the rainfall. There is radiation of there is solar radiation, incoming solar radiation, and then outgoing long wave radiation. Part of it might be blocked by the clouds, etc. And these the solar radiation, and that is how much solar energy it is receiving from the sun, I mean incoming, and how much of it is outgoing. So these also have a bearing on the temperature of the lake. Then the lake might overflow. There might be it might be flowing out to different rivers or canals which may be connected with it, and then there is a depth profile. At different depths the different properties might change. Then there are these like it's possible that there may be snowfall in like in some places around the lake, as a result of which ice may form on the lake. Then as the wind blows, waves can be created in the lake, and according to the heights of the waves, the temperature profile might also change. There can be shear stress as the water is flowing, and as a result that might also have some bearing on the temperature and so on. So like they have developed this kind of a very elaborate models, the model has so many different modules. Each of these modules they pass on, they have their, first of all they have their own parameters, and they they exchange information between the different modules and so on. So like as you can understand, this is a very highly complex and elaborate model. Now the aim is and simulating it will also require like a lot of time and a lot of observations, so like and lots of parameters. So this has been perfected for maybe one lake for which we have a lot of observations by like a meticulous deployment of sensors of various kinds. Now however this model is supposed to be a general lake model, so that it should be applicable to any lake even if we do not have all these observations. So the aim here is to see if machine learning can emulate this kind of the general lake model. So that is what we will see in the three very related papers which we will discuss one after the another now. So the first paper, process guided deep learning predictions of lake water temperature. The rapid growth of data in water resources has created new opportunities to accelerate knowledge discovery with the use of advanced deep learning tools. Hybrid models that integrate theory with state-of-the-art empirical techniques have the potential to improve predictions while remaining true to the physical laws. This paper evaluates physics-guided deep learning hybrid modeling framework with a use case of predicting depth-specific lake water temperature. The PGDL model has three primary components: a deep learning model with temporal awareness, that is a long short-term memory; a theory-based feedback which includes model penalties for violating conservation of energy; and model pre-training to initialize the network with synthetic data, that is water temperature predictions from a process-based model. The in situ water temperatures were used to train the PGDL model, a deep learning model, and a process-based models. Model performance was evaluated in various conditions, including when training data was sparse and when predictions were made outside of the range in the training data set. So these are various like ablation studies which is necessary to do in these kinds of things. Like when we are training a machine learning model to emulate the this kind of a process-based model, it is important that it should not require too much of training data, because we have already said that these models are expensive to run. So if you need too much of data for training the model, then that means that just to train the model you will have to run the process-based model lots of times, maybe lakhs or millions of times. Now if that you are doing anyway, then what is even the idea of having the machine learning model, right? So the model should be able to work quite well even by with a small amount of data that might be obtained by running the process-based model only a few times. The PGDL model performance was superior to the DL and PB for two detailed study legs, but only when pre-trained data included greater variability than the training period. The PGDL model also performed well when extended to 68 lakes with a median RMSE of 1.65 degrees Celsius, So, like as I said earlier, the aim is to develop the model for one lake and then use it for multiple lakes. So, this is a like rough scheme of the model. The machine learning model being used in this case is a LSTM. So, as far as that is concerned, there is no great innovation in this paper. The innovation lies in the way it is applied. So, there are these drivers or the covariates which are being used in both cases. So, first, like on one hand there is the process based model, the GLM, with the general lake model which we just discussed, and parallel to that is the process guided deep learning model which is aiming to emulate it. So, this process based model is of course based on the concept of energy balance and water balance and so on. For that it has its own process equation. So, like from certain initial conditions it will produce its predictions, and then while we are training the neural network, it will receive the drivers as well as the initial conditions, and it will know that the what its ideal outputs will be, as that is the predictions by these process based models. So, accordingly the neural network will be trained, but while it is being trained, it is like just as it happened in this case, it is not only important to make the predictions properly, but it is also necessary to make sure that the predictions are satisfying the different laws of physics. So, that is why the energy balance, it's like, which is of course a very important concept in this in the process based models. We will have to see whether the like whatever values is being predicted by the neural network, whether they are maintaining the energy balance or not. So, we will define a loss function accordingly, which basically sees how much of discrepancy has arisen based on what the neural network predicted, the discrepancy in terms of energy balance, and then the aim is to, of course, to minimize this discrepancy, so that it acts as some kind of a feedback to the neural network, and then the neural network again like updates its weights and so on. So, here the settings are as follows. So, the observations are the in situ lake measurements at different depths, and the predictor or the covariates which we considered here are the air temperature, short wave radiation, long wave radiation, wind speed, relative humidity, precipitation, etc. So, in this model this model already shows how all these covariates can like influence the lake water temperature at the different depths. So, they are all provided as covariates. Now, the LSTM model is used for the predicting of temperatures. Because LSTM is used, because LSTM is a sequential model and it is necessary for the predictions to be temporally temporally consistent, and the trained it is trained using output from the GLM corresponding to the given input, and the physical consistency of the predictions are maintained across the vertical profile using the law of conservation of energy, using the like as a loss function. Okay, and so like then comes the validation part. So, like the RMSE that has been obtained, like at different temperature profiles, that is to say at different depths of the lake, this kind of thing has to be studied. So, they have compared the process based models in green. The red is just the deep learning. If you do not consider this energy balance loss function, just if you train a neural network to predict the output from the input. So, that is the blue deep learning, and red is that is red the deep learning, and this is a blue which is the proposed model, the process guided deep learning. So, as you can see, in many cases the RMSE is like they have calculated the error of prediction for the different models. So, like as you can see that in many cases, initially the error is high using the proposed model, but then as we receive more and more temperature profiles, that is the number of so training so here on the x-axis they are like basically comparing the training data, and if it shows that as we have sufficient training data, like this is the proposed model is able to achieve almost equal RMSE as the as obtained from the process based models and so on. And similarly, the here we have also like another similar study has been done for a particular lake called Lake Mendota, and they have come across similar results. Based on this study, we come on to another very related paper. Here, physics guided machine learning for scientific discovery and application in simulating lake temperature profiles. Now, physics based models are often used to study engineering and environmental problems. The ability to model these systems is the key to achieving our future environmental sustainability and improving the quality of human life. This article focuses on simulating lake water temperature, which is critical for understanding the impact of changing climate on aquatic ecosystems and assisting in aquatic resource management decisions. General lake model is a state-of-the-art physics-based model used for addressing such problems. However, like other physics-based models used for studying scientific and engineering problems, it has several well-known limitations due to simplified representation of the physics processes being modeled or challenges in selecting appropriate parameters. While state-of-the-art machine learning models can sometimes outperform physics-based models given ample amounts of training data, they can produce results which are physically inconsistent. This article proposes a physics-guided recurrent neural network model that combines RNNs and physics-based models to leverage their complementary strengths and improves the modeling of the physical process. Specifically, we show that a pgRNN can improve prediction accuracy over that of physics-based laws by over 20% even with very little training data, while generating outputs consistent with physical laws. So that way this paper seems to be an improvement over this paper. So here we see that actually the proposed model which is marked in this blue, it requires significant amount of training data to reach good performance, but here they are saying that even with 20% of the even with small training data, it is actually able to get a 20% improvement over the process based model, while it is also generating outputs which are consistent with the physical laws. An important aspect of our pgRNN approach lies in its ability to incorporate the knowledge encoded in the physics-based models. This allows training the pgRNN model using very few true observed data while also ensuring high prediction accuracy. Although we present and evaluate this methodology in the context of modeling of dynamics of temperatures in lakes, it is applicable more widely to a range of scientific and engineering disciplines where physics-based models are used. So this is this is basically the setting. So this is a lake, and there at different depths there are the temperature. So the main governing equation of this model here is this thing, that is the energy balance. So the lake has a thermal energy UT, so and then there is a heat flux, there is incoming heat and there is outgoing heat, F in and F out, and the change of this total thermal energy of the lake is the difference between the incoming and outgoing waves at any given time. Now whenever there is a change in the total thermal energy of the lake, that is reflected at the different heights in different ways. So let us say that at we have some initial conditions of that, or we have some initial estimates of the total thermal energy in the lake. Then we as heat that is, we have observations of incoming and outgoing heat. We see how this total energy changes, and as a result of it, how the temperature also changes at the different depths. So this is the the model. So as you can see, there is the LSTM cells, which using the storing the hidden variable. The hidden variable in this case is the cells, the H1, the cell state, etc. Like you can consider this to as to indicate the past values of the total thermal energy and so on. I'm sorry, I mean not the total thermal energy, but the temperature profile at any given point. So that is the temperature profile at any given point is passed on to the next time point, and the observations, the inputs at every time point are these x1, x2, which is basically the heat flux, and the what this model does is that at every point, based on the incoming heat flux, it tries to estimate the lake energy, which is again passed on to the next step. And there is a separate variable here, like u1, u2, etc. That maintains the time sequence of the total energy of the lake, and it is updated using the these energy fluxes, which is measured at every time point as inputs, and accordingly the cell states or the hidden states of the LSTM, they maintain the temperature profile, and like at the end of this process, there is some kind of a decoder model which provides us the temperature profile of the lake based on the hidden values of the LSTM. So when we are training this kind of an LSTM, there is as you can see, there is a dual loss function. LRNN is of course the usual error of prediction. I mean the predicted values, how different the predicted values are of the actual values. By predicted values, I mean the values of the temperature at the different depths. And additionally, there is the energy conservation loss, that is to say how much of energy, that is as far as law of conservation of energy is concerned, how much error has there been. So as you can see, from the total lake energy at every time step, that is being estimated by the model, and the input fluxes are also being provided at every time step. So ideally this change of lake energy should be equal to the heat flux, but has that actually happened, or is there an error? So that is what is measured by this part of the loss function. So this is the physics based loss, and this is the prediction loss. So based on that, again the model is trained so as to minimize this loss function, and this is what the simulations look like. So as you can see, over several days or over several months, like if we plot the time series of the temperature of the lake at a particular depth, so like we can see that what is shown in blue is actually what the observations are. Like obviously it's something like a periodic, because we know that the lakes, just like temperature is periodic, similarly the lake's temperature will also have to be periodic at the different depths. So they have compared the GLM, in green, that is the general lake model which we discussed earlier, and then a simple like an a simple RNN with in black, and the in red they have plotted the physics based RNN, which has about 2% of the training observations. The initial one is the pre-trained RNN model, that is this is the RNN model which is generated which is trained just for one particular lake, but for the target lake it has not received any observations. So that is the pre-trained model. And then for this particular lake which is being considered, if it is just retrained once on this particular lake, that is to say some of its different parameters are re-estimated once using the observations, then we see like near perfect performance. As you can see that this red curve here follows almost the blue dots almost perfectly, so that we can that is with only 2% of the observations it is able to fit so well. And so also they have calculated the error at different depths, and as we can see that at certain so this green is what we get from the proposed model, and red is what we get from the calibrated lake model, general lake model which we saw. And we see that at certain depths, for example in this case at certain depths the proposed model gives lower RMSE than what even the calibrated GL process based model could do. in other situations, so they have measured it separately in different seasons, and it is seen that in some seasons the proposed model performs as well as the general lake models. In some other situations it actually outperforms, especially in summer and fall. Okay, and similarly that is if you consider across all the seasons, then also we see that the proposed RNN this actually performs better at the estimating the temperature at different depths. So based on this the same topic, we have one more paper. Here the aim is to estimate the parameters, the physical parameters. So like here the aim is to find the parameter settings which allows the process models to replicate the observed values. This is not only for lakes, but this can also be done for river systems also. So this is not necessarily tied to the GLM which we considered. I mean, the GLM can be like this can be used for estimating the parameters of the GLM. Apart from that, there might be some process based hydrological models for river basins, for river flows also. So their parameters can also be estimated using this framework. So they have developed a STN or spatiotemporal network. Like this is not very different from the concept of these Markov random fields, the spatiotemporal Markov random fields which we talked about earlier, which has the age functions and so on. Of course, this is not a probabilistic model, so it does not have the age potentials. Instead, it has certain gating variables, and these gating variables are used to pass the data across the spatiotemporally neighboring locations. So the input is the various meteorological variables at a particular location I in a lake or a river system, and the output is some kind of target variable. In this particular case, in this particular paper, they have considered the water temperature at that depth or at that location as the as the output variable. And of course, what that output variable from the model will be depends on the parameter setting k. So let us say this is the physics based model. Input to it are the different covariates and so on. Its output is the water temperature at different depths, but those outputs are going to be different for different values of the physical parameters. So this STN model, this is actually learned to what it does is it learns a mapping, that is like if the model has a certain inputs of the covariate values, and then what parameters does it need to produce a particular output. That is the question that this model tries to answer. So let us say that it already knows what should be what is the ideal output, that is what is the water temperature at the different depths. It now it sees whether the model is able to actually produce those water temperature values or not for different choices of the parameters, and that is framed as the learning problem. So the then the what it does is it provides these parameters so that it it provides the physical parameter settings such that the physics based model will be able to use those parameters along with the initial condition to produce what is the desired or what is the true output variables, that is the water temperature. So it's like it's like fine tuning the model by choosing the parameters appropriately. And so after this is done, as you can see, this is again validated by measuring the temperature at different depths over a period of time, and it shows that, and they have shown that if they can provide if the parameters of the model are estimated in this particular way, then it is able to do a better job of the simulation. That is this temperature profile comes as close to the observations as or closer to the observations than what was earlier. So basically these three papers, in a sense, they are a bit complementary. So here the aim of the first two papers is to emulate the physics based model, which is the general lake model. And the third paper, what it does is its aim is to provide the optimal values of the parameters to this model so that it can perform well. The second paper actually shows that it is able to outperform the general lake model, while the third paper actually discusses a way in which the general lake model can choose its parameters or receive its parameters so that it will be able to perform better. Okay, so this brings us to the end of this lecture. In the following lecture also we will see some other ways in which these machine learning models, including the physics inspired machine learning, is able to or is used for emulating different process models. So till then, bye.